This video is about expectations of functions of random variables. We know expectation assigns numbers to random variables to some random variables. Those numbers are their expected values or expectations. We also know some functions of random variables are still random variables and they have their own expected values, expectation. In this video, we look into expectations of functions of random variables and show how they are linked together with the original random variables. In particular, this video we're going to discuss a very special function, indicator function. It's a simple function, but it's used everywhere. It's a building block for many studies, and you're going to see its presence in artificial intelligence, machine learning, almost everywhere. The first question, what is an indicator function then? Well, indicator function is a binary function. It only takes either 0 or 1, so it only takes two different values. And here, the indicator function of set A, normally we use the notation IA to denote such function. It's a mapping from a whole set, complete set S, to either 0 or 1. And A here is just a subset of the whole set. So this function gonna assign 1 for any elements from A, otherwise 0. It's a very simple function. But given even it's simple, it has already many different properties and very useful properties. Let's take a look at the first property. It's power invariant. So IA, this function to the power k, again a new function, right? It's exactly the same function of the original function. If this power k, this k is any positive integer. This is very easy to understand. Given 1 to any power k is still 1, and 0 to any power k, if k is a positive integer, right, it's still 0. So here, on both sides of this identity, they are the same function. Let's take a look of IA to the power k. And suppose now we have an element from S, small s. It's equal to IA given small s to the power k. If S is from A, we know it's going to be 1 to the power k, which is still equal to 1. If it's not from set A, this small s is not from the set A, then it's 0 to the power k. It's still 0, right? Which are exactly the same function. So both sides of this identity assign the same numbers to the same elements, and they are the same function. They are defined for the whole set S. The second property is also easy to understand. IAC, the indicator function of the complement of set A, is equal to 1 minus IA, right? Because now IAC only equals 1 if S is not from A and maps elements from A to 0. So here, on the left-hand side, IAC maps elements from AC. So S is not from A, then it's equal to 1. If S is from A, it's equal to 0. It's exactly equal to 1 minus IAS, right? Because when S is not from A, this is 0. 1 minus 0 is 1. If S is from A, then 1 minus IAS is 1 minus 1, which is equal to 0. So on both sides of this identity, still we have exactly the same function. Next property is the indicator function of A joined with B. I given the joint set of A and B is equal to the product of IA and IB. This is also easy to understand and also very intuitive because now we know IA joined with B is equal to 1 if S is from both A and B. So S not only from A, but S also from B. So both indicator function of A, IA, and IB, they are all equal to 1. 1 times 1 is still 1, right? And if this is equal to 0, then either S is not from A or S is not from B. In this case, IA is 0. In this case, IB is 0. At least one of them will be 0. So the product is 0. Therefore, on both sides of this identity, right, they still represent, on both sides, they still represent the same function, so they are equal to each other. Given the third property, we already discussed the interception, the joint set. Next, of course, we're going to discuss the union. Well, the union is slightly complicated compared the aforementioned three properties. But the inequality here is very easy to understand, right? Because the right-hand side of this inequality here is always larger than the left-hand side. Because no matter what values, if the left-hand side is equal to 0, this holds true naturally. If this left-hand side, right, if there is a S such that I, a union with B, is equal to 1, then either IA or IB, at least one of them will be equal to 1. And sometimes both of them will be equal to 1. And together they're going to be 2. So they takes value either 1 or 2. And it's always larger or equal to 1, right? But how do we prove the identity here? We can pause the video for a moment and think about it. The proof can be done very easily if we combine the second and third properties together. Let's take a look at the solution now. The interception, the indicator function of the union A with B from the second property, we know it can be rewritten as 1 minus I given the complement. We know this set can be rewritten as the interception, the joint set of AC and BC. It's the same set, so here from this step to this step, we only rewrite the format of this set. It's still the same set, so together it's still the same function. Now if we apply the third property, we know I given the joint set is the product of the indicator function of individual set, right? It's going to be IAC times IBC. Let's apply the second property to IAC again. And we know IAC can be written as 1 minus IA. If we apply the same thing to IBC, we know it can be written down as 1 minus IB. Again, on both sides, here and here, they are the same function. We're almost there, and the last step is simply do a function. This is a function of functions, right? IA and IB, they are functions. 1 minus IA, 1 minus IB, they are still functions, and product them together is still functions. And now we only need to do calculations concerning functions of functions. So 1 minus IA times 1 minus IB, which is equal to, inside is 1 times 1 is still 1, then minus the function IA minus the function IB plus the function IA IB. Now, if we remove the brackets and change the sign of the plus and minus, one cancels each other, and what's left is the final result. Of course, if we rewrite, we can also rewrite this final result as IA plus IB. By applying the third property, we know the product of A and IB is equal to I given the joint set of A and B. Now, if we look at this formula, we must have seen something similar in previous studies. And indeed, we have, which is the inclusion-exclusion principle with two random events. If we compare the structure, we're gonna see they have exactly the same structure here. And indeed, if we don't take into account the overcounting, right? This is smaller or equal to IA plus IB. This is also smaller or equal to PA plus PB. They two have such similar structure, there must be a way to link them together. And in later discussions of this video, we're gonna show how these two are linked together, which is the fundamental bridge. They are linked together by the fundamental bridge. Before we introduce the fundamental bridge, let's summarize a little bit what we have just discussed. We noticed that IA is a function and it has some very special properties. Let's take a look. It can also be a random variable, right? If we consider A a random event. And if we take random event A to be a random event generated by random variables, this indicator function, it can be also regarded as a function of random variables. It depends on how we choose this set A. If we regard A as indeed a random event, then IA is a random variable follows Bernoulli distribution with successful rate PA, because now this random variable IA only takes one if event A occurs, and we know event A occurs with probability value PA. So this follows a Bernoulli distribution PA, right? Either equal to 0 or 1, only equal to 1 with probability value equal to PA. Now we start to link IA now with some probability value. And we have learned that expectation of a Bernoulli distributed random variable is equal to the successful rate. This is the fundamental bridge. If we look at this identity, notice that here on the left-hand side of this identity is the probability value. And on the right-hand side of this identity is the expected value of an indicator function. So now we link expectation with some probabilities. From the previous discussion, from the definition of expectation, we know distributions, they determine expectations. But now from the fundamental bridge, expectations can be used to recover probabilities of some random events, right? So on the other hand, expectation can somehow lead to probabilities. This is the fundamental bridge. Let's take a look how it can be regarded as a function of random variables. We can look into events associated with arbitrary real-valued random variables of the type x minus x, right? Now, this indicator function, given set x minus smaller or equal to x, is a function of x, and also a random variable, and takes value 1 only if this event occurs. X smaller or equal to small x occurs, otherwise it's equal to 0. Now we can use expectation of such functions of random variable to recover the distribution of any real-valued random variable x. Because now, if we know the expectation, if we know all the expectations of such indicator random variables with all possible values taken from the real line, if we know all the expectations of such random variables, then we can recover the whole distribution of any real-valued random variable x. So distributions determine expectations. Now there's also a way, by fundamental bridge, we can work with expectations to recover probabilities. So indicator function now is very useful, and let's take a look at some important results derived with these indicators and the fundamental bridge. The first result, well, we have already just mentioned. Apparently, a structure closely related with the inclusion-exclusion principle. So we're gonna prove inclusion-exclusion principle with the indicator function. First, let's consider the simple case. We have already seen that actually. Two random events A and B. Now, from the fourth property we have just discussed, we have this relation, right? Let's take expectations on both sides, on all sides actually. And from the fundamental bridge, it gives directly, well, the expectation of I of the union of A and B is essentially the probability of A union with B, right? Because this is a Bernoulli random variable and equals 0 with this probability, but we don't care this part anyway. It's gonna be 0. And plus 1 takes 1 only if A or B occurs. So probability of A union with B, which is essentially equal to the probability of A union with B, the fundamental bridge. And now we apply the expectations on all sides, and this is the result we have. So indeed, the indicator function, the relations with indicator functions, the relations among indicator functions directly lead us to the fundamental, the inclusion-exclusion principle concerning two random events. And the inequality here also shows that if we don't take into account the overcounting, we will have a larger value here, right? So we have to take into account the overcounting part to have a identity. This is a case with two random events. Now let's see what happens if we have n random events. You can pause the video at this moment and think about the steps how to prove this case. The inclusion-exclusion principle concerning n random events, and we can apply similar strategies here. Well, the result is quite straightforward actually. So let's consider 1 minus the indicator function of the union of all AIs. Why we look at this? Because now we can work with the indicator function of the joint set of all their complements. With the complements, we know the indicator function of the joint set is equal to the product of each AIC, right? It's going to be the product of each AIC from 1 to n. And for each of these products, we know for each AIC, it can be written as the product of 1 minus IA, which is equal here, right? So apply the properties of the indicator functions. Now we arrive at this stage. The next thing is just some simple algebra. Let's expand these equations. Well, we know it can be written as this format. And we know the product of indicator functions can be written as indicator functions of the joint set, right? Okay, so now we know if we look at the side on the both sides here, we can see that this indicator function should be equal to this monster. Then what is the expectation of the indicator function of this union? That is essentially equal to the probability of the union according to the fundamental bridge. And what happens to this monster here within the big brackets? Well, taking expectation and the fundamental bridge leads us to this. So now we prove the inclusion-exclusion principle. This is the inclusion-exclusion principle with the help of indicator functions. So this is the first important results we discuss in this video that can be derived with indicators. Let's discuss the second case. Before we discuss the second case, that indeed, again, we also have the inequality here, right? Because apparently here the indicator of the union is smaller or equal to the summation of all the indicator functions, right? Because if the left-hand side is equal to 1, then at least one of the indicator functions on the right-hand side is equal to 1. So the right-hand side is always larger or equal to the left-hand side. This also stresses the importance to correct for the overcountings. And that's why we always need to minus, plus, minus, and so many complicated parts, right? Okay, what is the second result we want to discuss? We want to discuss a different way of calculating expectation of x if x is a non-negative integer values random variable. We're gonna show that there is an additional way of calculating the expectation of x. We're gonna work with the survival function. Okay, this is the results. So let x be a non-negative integer values random variable. So x only takes value as a 0, 1, 2, 3, those non-negative integer value. Then the expectation of x can be written in this way, which is a summation of survival function values evaluated from 0, 1, 2, 3 until infinity. And the survival function here is 1 minus the CDF function. So gx x is essentially equal to the probability value of x that is strictly larger than x, right? Because it's 1 minus the CDF function, which is the probability of x smaller or equal to x. 1 minus this probability is equal to the probability of the complement event, which is random variable x is strictly larger than the small x. So how do we prove these results? Now you can pause the video at this moment and try to figure the steps yourself. The proof is kind of straightforward once you notice the trick. We're gonna decompose the x as a function of multiple indicator random variables. Right? Indicator variables, they can be regarded as a function of random variables, but at the same time, we can also decompose random variables as a function, as a summation of multiple indicator random variables. You can pause the video at this moment and try to figure it out how exactly we're gonna decompose the x random variable. Well, note that this random variable can be rewritten as a summation of indicator functions, a summation of indicator random variables. Now I claim the left-hand side is exactly the same random variables of the right-hand side. Why? Well, we know random variables are functions, right? From S to some numbers. And here we know X only takes non-negative integer values. So we claim that both sides of this identity, they map the same elements from the same outcome to the same numbers. Let's take a look at this. Suppose we have a S from the sample space that XS equal to a arbitrary non-negative integer M, right? So M is just one natural number. It could be 0, could be 1, could be 3. What happens to this summation then? This summation of all the indicator functions are still a function. And what happens to this summation? Let's take a look at the summation. The summation will be I from the positive integers xs larger or equal to I. So this indicator function here only equal to 1 if xs, if this m is larger or equal to I. Then how many ones we're gonna have in this summation? We're gonna have at most, we're gonna have actually exact m ones within the summation, right? Let's take a look. So I gonna from 1 to m. We know m is larger or equal to I in this summation. And for any I that is larger than larger or equal to strictly larger than m, we know I gonna be strictly larger than m, those gonna be 0, right? So we can discard those. And how many ones here? Exactly, we're gonna have m ones. So indeed, the right-hand side also map S to the value m. So on both sides, we have exactly the same function. Of course, you might wonder what happens if m is a 0, right? What happens if m is equal to 0? And apparently here, xs won't be larger than any positive numbers. So all those indicators gonna be 0. So for any values we discuss over there, right? It's always be 0 if xs is equal to 0. So both sides are the same function, and they are the same random variable indeed. What's the next move? The next move is kind of straightforward. We're gonna work with the fundamental bridge. So this above holds true because on both sides they are the same function, right? From S to the set of non-negative integers, and they are the same random variables. Now we're gonna apply the fundamental bridge. Let's take expectation on both sides. And we know this is the expectation of x. Now we have the expectation of x. And here we have the summation of probability x strictly or larger than I. But take a look at this. Take a look at this event. This event, given the fact that x only takes non-negative integers, we know this event is equivalent in this format. X is strictly larger than n minus 1. So this summation can also be written as the probability of x strictly larger than n minus 1. Now let's use n minus 1 equal to j. And we know this n minus 1 gonna starting from 0, right? So j from 0 to infinity. And now we replace j with I again. It can be rewritten as this summation. And what are these values? Oh, surprisingly, they are just the survival function value of x evaluated at the value I, so jxi. Then with the indicator function, with the help of indicator function at the fundamental bridge, we deliver another way of calculating the expectation of random variables if the random variable is a non-negative integer valued random variable. And the trick here is we decompose this x as a function of multiple indicators. This is the second important result we discuss here. So we can see that indicator function indeed is a very useful tool for proving some technical results, but it's also very important tool to solve some simple, some similarly complicated probability questions, right? Let's take a look. How do we apply the indicators to simplify some questions? Now we already seen this one example, so we're gonna apply a similar tricks. We're gonna again decompose some random variables as a summation of indicator functions. Okay, and this is a very important trick of applying indicators to solve real problems. So let's consider this challenge. There are n visitors and n different balls with n balls with their names on. So if we let each visitor pick one ball randomly, and then they keep the ball, denote the x the number of a match. By a match, I mean the visitors gonna picking exactly the ones with their own names on. So the visitors, they gonna pick the correct ball, while some visitors may pick the wrong ball. Some visitors pick the correct ball with their own names on. What is the number of such matches on average? So what is the expected value of x? You can pause the video at this moment and try to figure out how to tackle this problem yourself. Well, again, we're gonna apply a similar tricks. Let it denote AI the event that ith visitor gets the correct ball. Then apparently x equals to the summation of indicators function of AI. So if AI occurs, we know this equals to 1. And how many ones we have is exactly the number of visitors get the correct balls. So the both sides is exactly the same random variable. How do we proceed from this step? Naturally, it's gonna be the fundamental bridge. Right? Because now if we take the expectation on both sides, we know the expected value. Well, let's take a look. Let's take expectations on both sides, then the expected value of x is the expectation of the summation here, IAI. Because now we are only working with summations of finite terms, right? Finite bounded terms. IAI is always smaller or equal to 1. It's sometimes equal to 0. But anyway, it's a summation of finite bounded terms. And it's safe to say that we can interchange the order of the expectation and the summation according to the linearity of the expectation. When the expectation is well defined, we can safely do this. And what is the expectation of IAI? Is essentially equal to PAI, fundamental bridge. Now to solve the expected value of x, we only need to solve for PAI. Well, according to by symmetry, we know each visitor is equally likely to get the correct balls, and given there's n balls, for PAI is simply 1 over n. And the summation of n, 1 over n, is simply 1. So on average, there will be one visitor. On average, we expect one visitor to get the correct ball. If we look at the question itself, it looks very complicated, but once we apply, once we get the help from the indicator function, we can solve everything in a pretty straightforward and intuitive way. So this video basically discusses the importance of the indicator functions, what is indicator functions, and how can we work with it. It shows that with the help of indicator function, we link directly the expected values with probability values. And there's many important results that can be easily derived with the indicator functions. If we don't apply the tricks, it can be very messy, but once we get the help from the indicator random variables, indicator functions, everything can be solved in a much easier way. Hope you enjoy it, and thank you for watching this video.